So yeah, I'm going to talk about volcanic lightning and how we're using it for remote sensing of explosive eruptions. I'm an NSF postdoc fellow at AVO. I've been here just under a year now. So a lot of the work I'm going to show today is part of this postdoc project, and so it's a lot of preliminary results at this time. So I'm really looking forward to getting your guys' ideas on this project at the end of it and really having a conversation, because none of my results are set in stone yet. So it's a really exciting time to be presenting this work. Oops, let's see. There we go. So this talk is going to be divided into 4 main sections. I'm first going to talk a little bit about general lightning, how it forms, some of the vocabulary that goes along with that, just so we can all get on the same page. I'll then talk about volcanic lightning specifically for a little bit and how volcanic lightning uses some of the same terminology as general lightning, but also there's some different classifications and charging involved. I'll then talk about 2 different case studies, Volcanic, which is the focus of my postdoc project at this point. And then at the very end, I'll touch on some work done at Anak Krakatau with the eruption in 2018 and how that's informing some of the work I'm doing at Volcanic and kind of bring it all together. So to start with the general lightning, lightning is the transfer of charge between 2 oppositely charged regions. And this happens by the air electrically breaking down so that charge can transfer. And so this happens in a series of steps. It's not an instantaneous process. So the first part of lightning generation is called the stepped leader. So lightning actually feels its way to the ground. You can think of it that way. So you have a negatively charged cloud, positively charged ground, and the lightning is moving in all these little jumps and steps trying to feel its way to the oppositely charged region. Once it connects to the ground, you get what's called a return stroke. And this is the visible flash that most of you probably associate with lightning. So that visible flash is the massive exchange of charge between the 2 regions. So in this example GIF here, you can see the negative charge from the cloud flowing into the ground. And it froze. Oops. Okay. There we go. Sorry about that. My computer froze for a minute. So with general meteorological lightning, there's really one main type of charge that is occurring in the clouds, and that's charging between ice and grapple. And grapple is just a fancy word for soft hail. So grapple forms in the upper part of the cloud, and ice crystals are forming in the bottom. But the ice crystals are really light, and the grapple's really heavy. So they're going to be exchanging places in the updraft and the flux within the cloud. And when they exchange places, they're going to interact with each other and charge. And so briefly, the ice particles charge positively, the grapple charges negatively, and you get these charge differentials that allows lightning to form both within the cloud and between the cloud and the ground. And these are the 2 main types of classifications for lightning in meteorology. You have cloud to ground. So that's this image here on my left, is a cloud to ground stroke taken in Tampa Bay, where I used to live. And then on the right, you have a cloud to cloud flash. So this is where charge is being transferred between 2 clouds, and it never actually connects with the ground at all. You can also have inner cloud, where the charge is just being transferred from one section of a cloud to another. So that was super fast overview of general lightning. But really what the main things I want you to remember is that lightning is composed of stepped leaders and return strokes. There's the IC/CC in cloud, and then there's the CG, or cloud to ground, types of strokes. And then it's ice and grapple charging is the main mechanism for meteorological lightning. So how is this different from volcanic lightning? So for volcanic lightning, we're going to talk about some overviews on why we actually care about volcanic lightning at all. It's always a good place to start in a talk, I think. We'll then talk about some of the types of charging involved, because we do have some different charging happening with volcanic lightning compared to just meteorological lightning. And then I'll talk about detection methods. So how are we actually measuring volcanic lightning out in the field? So general volcanic lightning, why we care comes all the way back to this classic figure by the USGS of all of the hazards associated with a volcanic eruption. So we have different methods for monitoring these already. So we have satellites, we have seismometers, we have infrasound. But one of the main things we're hoping lightning can help give us more information on are these two areas. So where is ash falling? We know that lightning has a relationship to ash in the plume, so maybe it can give us some information on where ash is actively falling out. And then information on the eruption column. So, and the actual eruption source parameters of the eruption. So a lot of photography has happened of lightning in the eruption column, so we're figuring there's probably something there. And here are some of those photos. This is mainly just eye candy here for you. These are 4 large-scale eruptions with volcanic lightning that was captured by photographers. So we have everything from a VEI2 eruption at Sakurajima all the way to Kelbuko and Chaiten with these gorgeous lightning displays. So it occurs all throughout the plume and the eruption column. And my goal is to figure out what can lightning actually tell us, if anything, about these regions. So with meteorological lightning, I've said that we classify it based on where the charge is transferring, so cloud to ground or cloud to cloud. With volcanic lightning, we do it a little differently. We divide it into 3 different categories when we talk about lightning. So the first one is a continual radio frequency impulse. So that is a huge mouthful. So we just sum it up as CRF. That's how you'll see it referred to in the literature if you dig into this. CRF is a really interesting signal. It's not technically lightning, but it's an electrical signal that we can record with some of our instruments. And it's unique to volcanoes. The signal isn't seen in meteorological thunderstorms. And the study of CRF is really what has catapulted volcanic lightning and volcanic electrification studies into the mainstream. However, for this talk, I'm not really going to focus on CRF. I'm going to be talking more about the other 2 types. So we then have near vent lightning. This is lightning that's occurring in the eruption column or near the jet. It can sometimes actually connect to the edifice of the volcano, similar to a cloud to ground stroke, but it's really all concentrated in that highly turbulent, highly energetic eruption column. We then have plume lightning. So plume lightning is the most similar to meteorological lightning in scale. And we also think that ice may play a factor in this type of lightning. So those are our 3 general categories of volcanic lightning. So moving on to the types of charging. Volcanoes are different from meteorological thunderstorms in the one main way that there's silicate particles involved. It's not just ice and water in the cloud. And these silicate particles can interact in different ways and release charge and formed charge particles. So the first type of charging that can happen is fractoemission charging. So this is where you have a particle. So in this case, that's my turquoise sphere here on the page. And if you imagine that as a chunk of solidified magma, during the eruption, it may fragment and break apart. And when it does that, it can release charge into the plume, and then these different particles can be differentially charged as well. We then have triboelectric charging, which the literature suggests is really important for the charging of the volcanic eruption column when you have all of that ash interacting with each other. Because what happens in triboelectric charging is you have 2 particles, my 2 blue spheres here, and they're gonna interact with each other. And when they collide, they transfer charge. And research done by Ford et al. In 2009 has shown that the preferentially larger particle will become positively charged, whereas the smaller particle will become negatively charged. And then these different size particles can gravitationally separate and form different pockets of charge throughout the eruption column. So triboelectric charging is really a main driver of charge generation within the volcanic plume, especially that near jet column region. We also, again, have ice and gravel charging. If the plume gets to an altitude where it can actually get cold enough to form ice, this is typically around -10 to -20 degrees Celsius that you start getting ice formation on ash particles. We can see this same kind of charge separation and lightning generation that we saw in meteorological lightning. And this is what we think is most likely happening with these large plume lightning flashes that occur in the umbrella cloud decently far away from the volcanic vent. We think this ice and gravel charging is really a predominant method of charge generation for these plume lightning flashes. So finally, in volcanic lightning section, we're going to talk a little bit about the detection methods. So how do we actually study volcanic lightning? So the first way is through photography. So volcanic lightning has drawn photographers for pretty much as long as they've been able to capture it on the cameras. The first written record of volcanic lightning was actually in 79 AD with Pliny's record of Vesuvius. He mentions lightning there. And so lightning's always been around. People have talked about it, but it's really hard to record. And photography is a great way to do it, but there are drawbacks. And one of those is illustrated here. So these 5 images are still frames from a high-speed video record of Sakurajima from my dissertation in work in 2015. And on the right-hand side, you can definitely pick out lightning. There's definitely lightning in those 2 frames. However, when you start looking really close at individual frames, there's actually lightning in all 5 of these frames, but some of it is really faint. Some of it, like this upper right-hand side here, you can see this is all one flash, but we lose the middle because of the opaqueness of the eruption cloud. And so this is one of the problems with photography, is that you do miss information. You're not going to get a full, complete picture of the lightning occurring in the plume. So what do? So instead of using photography, we turn to the electromagnetic radiation that's actually emitted from lightning when it's generated. And this occurs across a wide range of frequencies, all the way from 3 kilohertz to 300 megahertz. And different portions of the lightning emit different radiation. So for example, that stepped leader that I showed at the beginning, that this GIF should hopefully be replaying for you, each one of those steps is releasing a burst of very high frequency radiation. So that's VHF. So that's 30 to 300 megahertz range. And we can record that with a lightning mapping array if we have one set up within approximately 200 kilometers of the volcano. So this is a local near volcano method, but it gives highly detailed images of lightning flashes in 4D. Alternatively, if we don't have the ability to set up a local network, we can use the radiation from the return stroke. So that visible flash that you see with lightning emits not only visible light, but it also emits radiation in the VLF, so the very low frequency range. So that's 3 to 30 kilohertz. And this very low frequency energy actually can radiate very far from the volcano, bounce off the ionosphere, and travel up to approximately 4,000 kilometers away from where the flash happened. So this allows global networks to be put into place where you can have 60 to 100 sensors distributed globally and record lightning wherever it occurs. So there are 3 main global networks that we use in volcanic lightning studies. Those are the Worldwide Lightning Location Network, ran by the University of Washington, Earth Networks, and then the GLD 360, so that's the Global Lightning Data Set, and that one's ran by the company by Sala. And so these global networks are really exciting for remote monitoring of volcanoes, because you don't have to rely on knowing a volcano is going to erupt or thinking it's going to erupt and setting up a local network. They're just always running. They monitor lightning for meteorological uses, And so they also just happen to catch volcanic lightning. So brief overview of what I'm hoping you'll remember out of this volcanic lightning section is that there's 3 classifications: CRF, near event lightning, and plume lightning. There's 3 types of charging: fractoemission, triboelectric, and that ice grapple charging. And that there's 2 main detection systems that we use. There's the VHF, which we use on local scales for highly detailed data. And then there's the VLF, which is used on global scales, which is really helpful for remote monitoring. Okay. So moving into some of the case study work, I'm going to first talk about Rakoki. So Rakoki, we're going to go through and talk a little bit about some infrasound work that's been done, some plume modeling I've been working on, and then a preliminary spatial analysis that I've started to try and understand the lightning grouping a little bit more. So starting with just general basic background on Rakoki. It's a very small volcanic island that is located in the Kuriles, so that's south of Kamchatka, north of Japan. And this is an image of the volcano. It's about 2.5 kilometers square and about 0.5 kilometer tall. So this is a very, very small volcano, and it has no in situ monitoring equipment on it. There's no seismometers, there's no infrasound, there's no ash collection device, there's nothing on the volcano itself. So everything for monitoring this volcano has to be remote. Rakoki, the eruption that we're looking at specifically, occurred last summer between June 21st and 22nd of 2019. The previous eruption from Rakoki was all the way back in 1924, and then the one before that was in 1778. So it doesn't erupt all that often. However, all 3 of those eruptions have been BEI4. So when it does erupt, it's a pretty strong eruption. So talking a little bit about the infrasound, the first thing I'm going to show you is a video that hopefully will work. And what this video is going to show you is the Himawari satellite data in the visible band overlaid with lightning detections. So polka dots are red and blue. Those correspond to positive and negative charges. The size of the dot is the strength of the stroke. And then the sound that you're going to hear is the infrasound that was recorded and then sped up so it could be in human hearing zone. So hopefully this works. I'm just going to let it play through. So it's about 30 seconds or so. Okay, so hopefully some of the things that you'll have noticed in there is that there were several different plume events in this eruption. It wasn't just one large plume forming event. And that the infrasound and lightning kind of seemed to go hand in hand during this eruption. So I mentioned that there was no in situ monitoring equipment on Rakoki. And so this infrasound data came from the Comprehensive Test Ban Treaty Organization. We used these 3 infrasound arrays, which ranged between 600 and 1700 kilometers away from Rakoki. And my colleagues Kathleen McKee and Sean Mayer did an amazing job processing all of this infrasound data, and were able to turn it into this beam-formed infrasound signal. So what we're seeing on this plot here, this black squiggly line is the infrasound. And then the white line down the center of that, so you can see my mouse horizontally down the center, those white points are the coherent signals with a back azimuth to Rakoki. So that's indicating that these are eruption signals being recorded. Each of the vertical lines is a lightning stroke recorded by the GLD, and they're color coded by distance. So it ranges from 0 to 61, that might be under the video. So the yellows are in the 50 to 60 kilometer range away. But you can see quickly from looking at this that most of the lightning stayed pretty close to the volcano within about 15 kilometers until you got to this large pulse in the middle. You also can see that, like we saw in the satellite imagery, there's a series of pulses of activity that's really clear in this infrasound. Now I've just labeled them here. There's about 11 of them. And if we look specifically at the first 6, we can really see that there's a relationship, it appears, with how long the infrasound is occurring for with how long the lightning is occurring for. So if we look at pulses 5 and 6 in particular, we get lightning strikes at the same time as infrasound detections. Infrasound turns off and lightning turns off. And then we get a gap and then it repeats. So one of the things I was interested in looking at here was, is there an actual quantifiable relationship between the infrasound duration and the duration of lightning being generated? So quick plot of this. So we have lightning duration on the y-axis, infrasound duration on the x-axis, and I just plotted up for each one of those pulses. And we can see that there is a really nice relationship forming here. However, I'm always a little weary of correlations when you only have a handful of points. So I was thinking about how can we make sure this is a real relationship that we're seeing. And one of the things that came up is some work I did with my dissertation at Sakurajima. And so this plot here is a little complicated. Don't worry, I'm going to walk you through it briefly. So this is an effect plot. So it's the output of a model that I built for my dissertation. And so on the y-axis, we have the duration of electrical activity. Same kind of thing. How long was the plume electrically active? Each one of these panels is a different infrasound duration. So we go from 30 to 100 seconds. And then the x-axis on each panel is the same range of seismic energies. So the main thing I want you to notice here is that as we move from left to right across the panels, we're increasing infrasound duration, and the duration of electrical activity is also increasing. And so we're seeing that same trend at a different volcano with a different model. And the Sakurajima model was made with hundreds of events, so it really gives weight to the idea that this relationship is real and that lightning duration and infrasound duration are intimately tied. Going to do some shameless self-promotion here. If you're interested in that model, that paper was recently accepted at JVGR. It's in pre-proof form right now. You can go read it, or it should be in production form in the next week or two. So shameless self-promotion there. I'm pretty proud of this paper. So overall conclusion from volcanic lightning and infrasound is that the durations of these two signals are positively correlated across a wide range of eruption size. So VEI2 Sakurajima eruptions, we're seeing this relationship all the way up through this Reikoki VEI4. So moving on to some of the plume modeling that I'm doing. This is, again, we're starting to get into preliminary results here. So keep your minds open for ideas. I'd love to hear them at the end. So the first thing I did for Reikoki was I determined the plume height throughout all of the eruptions. I did that using the band 13 Himawari data. So what we're seeing here, it's a bit coarser of a pixel size than the visible band that we saw earlier. And I was able to take the lowest temperature in the plume and convert it to an altitude. And then I was able to use those altitudes to run plumeria models. Plumeria is a 1D model that gives you information on plume temperature, plume density, several other parameters for each pulse here. So I'm mainly going to talk about the temperature and the density. So this first plot here is the plume temperature with altitude. The dashed line is the air temperature, so ambient air. And then the dotted line is just demarking negative 20 degrees Celsius. So you might remember from the beginning that negative 20 degrees Celsius is that temperature where we think ice is going to start to form on ash particles in the plume. And one of the interesting things we can see here is that pulses 10 and 11, so those final two pulses, were incredibly small. They had very few flashes, but they don't even reach -20 temperatures. So they're warmer than that the entire time. So all of the lightning from those two pulses is likely generated by fractal or triboelectric charging in the plume, so that silicate charging process. The rest of the pulses do hit the -20 level, but interestingly, you can see that it doesn't happen at the same time as the air. One of the assumptions that we've made in the past is that the plume cools relatively along the same line as the air, so when you hit the ambient air temperature at -20, the plume is likely also that temperature. But here we're seeing that in our largest pulse, pulse 7, it actually doesn't reach -20 until a solid 4.5 kilometers higher in altitude than the ambient air. So I haven't really dug into this too much more than that, but it's a really interesting little nugget of information that I think will be really helpful for determining if ice or ash charging is relevant in the plume at different locations. Moving on to the plume density output. So again, this black dashed line is the air density. And using this data and where the plumes are crossing back and forth over air density, we can determine the altitudes of different components of the volcanic plume. So where is the jet? Where is the level of neutral buoyancy? Where is the umbrella cloud forming? All of those things. So what I did here is I looked at those values for all 11 of the pulses, kind of averaged them together, and then built this gradient over top the wind model. So we have the jet region way down at the bottom. This region is only at max 2 to 3-ish kilometers, but mainly 1 kilometer is like really strong jet region of the plume. We then get a level of neutral buoyancy that averaged between 8 and 10 kilometers across the plume. And then the umbrella cloud was forming in the 10 to 16 kilometer range. So our highest altitude plume was about 16 kilometers. So this plot here is really interesting when you look at the wind, which are these black lines. So we have the azimuth is the thin black line, and then the two thicker lines are the actual speed of the component. So we can see that the jet region is occurring where the wind is pushing generally northwest, and then the rest of the plume is in an area where the wind is pushing east, and that's going to come back up in the next section. So just keep this plot in your head. So one of the other things that I've started working on is looking at the mass eruption rate in relation to lightning. So this plot is pretty busy. I'm going to try and simplify it down. I calculated the mass eruption rate using the bent plume area code, the Puget equation from 2016, as well as Maston's equation from 2014. So those are all of the black dots. And then the red asterisks are the stroke rate per 10 minutes of the eruption. And if you squint at this, I can convince myself that we're seeing the mass eruption rate generally increase over the course of the eruption through those first 6 pulses, peaking at pulse 7, and then starting to decrease again. And we're seeing a similar relationship with the stroke rate. So as stroke rate is increasing, mass eruption rate is increasing, we're moving towards that large pulse 7, and then it tapers back off again. So to try and quantify this a little more than drawing clouds on this plot, I've directly plotted mass eruption rate and stroke rate against each other. And this is a messy plot. We don't see a really beautiful linear correlation or anything here. However, we do see a general positive trend between the mass eruption rate and the stroke rate per 10 minutes. And so this is an area where I really want to dig more down into this correlation and see if I can model it in a way that better demonstrates what might be happening with this relationship. So next conclusion is that lightning stroke rate may be positively correlated to the mass eruption rate. Overall, a lot more work needs to be done on my part to really flesh this section out, but it is an exciting initial result that we're seeing these light correlations. So moving into the spatial analysis section of Reikoki. So if you remember from that video at the beginning, there were 11 pulses. What I've done here is each one of these squares is one of those pulses with all of the lightning from that section, overplotted the largest plume from that time. And you can see really clearly here that the lightning is highly concentrated around the vent. It's not really extending out with the plume all that much, with the exception of stroke 7, which is this panel here on the 3rd row, and a little bit with 8 and 9. So one of the things I was interested in seeing is, where is the lightning located around the vent? Is it still traveling with the plume down, just closer to the vent? Is it directly just sitting on top of the vent? Where is this lightning really showing up? And so to do that, I used a couple different methods. The first one is I built a heat map of the eruption. So this is just a 2D density diagram. And this really shows that for the total eruption, so this is looking at all 753 lightning strokes, that the highest concentration of lightning strokes is actually about 10 kilometers to the northwest of the vent, which is interesting because the plume mainly traveled east the whole time. So there's some interesting thing going on here that we want to investigate. Breaking it down by pulse, we can see this even more clearly in these rose diagrams that I built. So for these rose diagrams, I looked at the azimuth of the lightning to the vent and divided it into the 8 main octants, so north, south, east, west, northwest, northeast. You get the picture. And counted them up like a histogram. So what we can see here, all 11 diagrams, with the exception of pulse 7, have the same scale. So we can see not only the direction of the lightning concentration, but which pulses had more lightning overall as well. And we see that all 10 pulses, except for pulse 7, the lightning has a peak concentration in that northwest corner. So again, we're seeing this majority of lightning occurring to the northwest, even though the plume seen in satellite imagery is traveling predominantly east. And so to kind of go into what I think is happening with Reikoki, we're actually going to look at another volcano. So the eruption of Anak Krakatau happened in 2018 between December and January. Krakatau is located in Indonesia, just north of Jakarta. And it's a highly populated area, and there was a ton of photography of this event. And that's something that's really lacking at Reikoki. We only have the satellite data, so we don't really get a side view of what's going on in the plume. But we do have that with Krakatau. And we see some similarities in these eruptions. So here's a satellite imagery from Himawari. So same satellite of the Krakatau eruption. Anak Krakatau is the yellow triangle. And we can see that the plume is moving predominantly west-southwest. And I'm going to point out that there's a small island to the east of Anak Krakatau. Here we are zoomed in on a sentinel image of this island. And this is going to play a big role in this analysis and this idea of what might be happening. So some colleagues, Sam Engwell and Sebastian Watt over in the UK, were able to actually go to Anak Krakatau and take ash samples. And they came back and they told me that almost all of the ash collected occurred on this island, and that there wasn't really a lot of ash on this westerly island, which is interesting when you look at the satellite and the plume is the plume is mainly traveling west-southwest. So if we take that and we look at the lightning concentration, we see that the lightning is also concentrated to the east. So this is similar to Reikoki, where the lightning concentration is in the opposite direction of where the main umbrella cloud is traveling. So what we have with Krakatau, however, is we have some beautiful photography of the plume as it's forming. And what we see in this image here is that at low levels, the eruption column is actually being pushed to the east, and we clearly see ash fallout happening over this small island. Now, what we don't see in this photo is what's happening above the frame of view. However, this lightning flash here gives me some hint that I think this plume might be bending back towards the west, and this flash would be a cloud-to-cloud type flash connecting this lower portion and the upper portion of the plume. And we can actually see this kink when we see an image taken with a wider field of view, where again we can see the lower portion of this plume at Anak Krakatau is traveling eastward, and when we hit a certain altitude, it starts traveling west again. And this matches with what we see in the wind azimuth data, where low altitudes, the wind is pushing east, and as you go up in altitude, it starts going west again. So if we go back to this diagram here of what we were seeing from our plume modeling at Raikoki, I think it's a similar thing that might be happening, is this lower region of the plume, this jet region, is traveling west, and we're getting a lot of ash fallout, and we're getting a lot of lightning associated with that ash fallout to the west. And then the larger umbrella plume is traveling eastwards, and we're not seeing as much lightning in that until we get the largest eruptions where we can get some of that ice and gravel charging again in pulses 7 and 8. So overall, the spatial distribution of volcanic lightning may be related to areas of intense ash fallout, which may or may not be in the direction of main umbrella cloud movement. Now, of course, there's other ideas on what might be happening here. It might have to do with pyroclastic density currents or turbulent structures within the plume itself. So this is, again, an area of active investigation, and I'm really excited to continue to explore what some of these options might be for this spatial distribution of lightning. So just to tie up, the 3 main conclusions of my research so far is that volcanic lightning and infrasound durations are positively correlated across a wide range of eruption sizes. So VEI2 to VEI4, we're seeing that these durations are intimately tied together. That the lightning stroke rate may be positively correlated to the mass eruption rate. This ties in with previous research that has been done, so I think this is definitely going to come to fruition with some further modeling and detailed work. And finally, that the spatial distribution of volcanic lightning may be related to areas of intense ash fallout. Thank you.
Thank you, Cassandra. That was excellent. We'll open this up now for questions. As I'm opening that up, I just put the Slack channel invite for those that want to look at that. And looks like we have some questions up already. Mark, you want to go ahead?
Yeah. Hi, Cassandra. Nice to meet you. That was a terrific talk. I have a question about some of the relationships you're playing with. The plot you showed of flash rate against mass eruption rate. Do you think that it's a simple correlation, that flash rate just increases? Or is the flash rate just large for mass eruption rates bigger than about 10 to the 6?
So that's a great question. My experience with my dissertation is that none of these relationships are going to be nice, simple, linear, clean relationships. So I feel like there's likely a threshold that needs to be dug out, and with the mass eruption rate where lightning will really skyrocket, I think that's highly likely. So I just haven't gotten to that part yet.
Right. The follow-up question that's related to another correlation you've been exploring, which is with infrasound. That's a neat thing to do. Do you find that lightning always lags or leads the infrasound response, and whether there's a consistent lag in time?
So this is, again, really cool question. So one of the things with this data set right now with the which comes first is it's actually about half and half. When you look at the infrasound detections that I currently have and lightning, there's about a minute in between when one shows up and when the other does. And between the 11 pulses, it's about 4 one way, 5 the other for the big 9 pulses. And one of the things that a colleague of mine suggested is actually to better model the infrasound timing back. So we just used the basic sound speed over 600 kilometers to determine the time of those duration, the time of the infrasound start. So I think if we work on better modeling what time the event started, it might be a little bit more accurate there.
All right, thank you.
All right, so we also have some questions in the chat, and I'm going to get to these in a second. I'll just sort of try to scan these. Okay, well, let's go with Yoshi Gilchrist's question. He has several here, and you can see them in your chat too, Cassandra, if you like. Okay. But Yoshi asks, how does the formation of ice crystals and graupel change when ash is present? For example, does ash serve as a predominant nucleation site for ice formation, and therefore pure ice crystals are less likely to form? Does ice form more easily with the presence of ash? And overall, does the presence of ash change the vertical distribution of ice crystals, graupel, in the cloud to be different than the meteorological sketch you showed? So this is a question that was asked kind of midway through your talk.
Okay. So.
And I can repeat parts of it if you want.
No, I pulled the chat up halfway through that. So, from my understanding of it, is ash is the main nucleation site for ice, and that's why we're seeing that -20 C as a really important temperature overall. There's been experimental work by, I'm blanking on the name. I can look it up, but there's been work done to show that that temperature level is important because that's when ice is starting to form on ash. As far as if the presence of ash changes the vertical distribution of the ice crystals, graupels in the cloud, I think it probably makes it a little bit more chaotic. There's a lot more turbulence in the volcanic plume than there is in a typical thunderstorm. Typical thunderstorms just have one main updraft in the center of the anvil. So you get one main updraft and down. So there's a lot more turbulent structures and eddies in there, so it's likely more complicated. I haven't done any modeling specifically in the ice-ash interactions, so I can't go any more in depth than that, but I would assume that it's way more complicated than thunderstorms.
Thank you. And I guess I have one little bit of a question that's related to that to myself. That is, I really like the result where you see the lightning kind of off direction from the main dispersal, particularly at altitude. I was wondering, with that observation combined with some of your plume modeling, do you notice a sort of critical sort of concentration of ash where you don't see much lightning above?
So I haven't done the ash modeling yet. So I haven't gotten to answering that question, but it's on the list of things that I'm really excited to look into, how the ash concentration aligns with that.
Cool. And so let's go back to the chat questions, and please feel free to raise your hand too if you have other questions. Okay, this is from Marissa Costa. She writes, does volcanic lightning sinter ash as it moves through the plume? And if so, does it make ash fulgurites?
So this is a really cool area of study. So if you're interested in this, I highly recommend some work done by Kim Genero. So she's done a lot of work on how lightning interacts with ash, and it doesn't form like a full fulgurite like you would find on the beach, but lightning does actually hit ash in the plume and it can completely vaporize the ash particle, Kim has shown, or it can make these really cool spherules where the ash is completely melted and then re-solidifies as pretty much perfect little spheres that we can then see in ash deposits. So yes, it can melt the ash and reform it in the plume, and Kim Genero's done an amazing amount of work on that. So I would direct you to her papers.
Thank you. Okay, so now we have a question in chat again from Karen Bosson, and she writes, do you find a preferential discharge polarity for near vent and plume lightning? Is there a change in polarity when ice comes into play? And then she has a subsequent question. Besides finding a correlation between infrasound duration and electrical signal duration, do you also see a correlation between the maximum acoustic amplitude and the electrical activity? For example, number of flashes, duration, magnitude.
So I'll take the first question first.
Sure.
So the polarity of the charges has been a really interesting head scratcher through a lot of this. So we have a lot of information on the polarity and then the peak estimated current of each of these strokes. That's some of the data that we get from the global networks. We really only get location, time, polarity, and strength. Peak estimated current is what I mean when I say strength. So that's in kiloamps. And I have yet to find anything in those numbers spatially or temporally with rates. So I'm playing around with it, but I'm not really seeing too much change in the polarity distribution or the estimated peak current of the flashes throughout the eruption. So I'm playing with it. I'm trying to find something because I feel like it should be there. But for the most part, it seems to be pretty random. And then second part. So correlation between maximum acoustic amplitude and electrical activity. So yes, so that paper that I shamelessly self-promoted has 5 different models that I built for Sakurajima. And in those, I look at the acoustic energy, the seismic energy, acoustic duration, and seismic duration in relation to flashes, CRF, and overall electrical activity. And overall, throughout the models, the larger acoustic energy there is, the more likely we are to see electric signals and the more of those signals that we'll see.
Thank you. Let's see. Any other questions on the raise a hand? Look, it doesn't look like it. Let's see. I think I have covered the chat questions, but pipe up if you have a question that I'm not picking up here. Looks like Yoshi has a follow-up.
Okay.
Thinking of conclusion 2 about volcanic lightning rate and mass eruption rate relationships. Have you looked at this relationship in terms of the ratio of erupted mass partition to pyroclastic density currents versus airfall from spreading ash clouds? For example, have you looked at eruptions that begin with a strong convective column delivering most tephra to spreading clouds and then transition to a partial or total collapse regime with more erupted mass delivered, spreading pyroclastic density currents? I'll stop there. There's further questions.
Okay.
I'll let you give a chance to answer those.
So no, in short. So we're just starting some of the modeling of this. So with the pyroclastic density currents, I was working on my AGU abstract this week, and a co-author on there suggested that might be a reason why we're seeing lightning to the northwest. So that's just recently come into my area of possibility. So I haven't done that. One of the problems is a lot of the volcanoes that we look at are really remote. And so we don't fully know what is happening and what regime they're in. So that's one of the things I'm working on figuring out with Ray Koki, and why eruptions like Krakatoa with the photography are so helpful to show what might actually be happening. So I have not done this modeling yet, but I hope to.
Thanks. Okay, so other questions, feel free to pipe up. I guess I have a question while people kind of formulate their ideas, and that is, given Ray Koki's remoteness, are you able to look at other satellite signals? Is for example, the Knox formation strong enough to detect through satellites from the lightning?
So we looked at Knox last summer during the CIDR workshop with Simon Karn, and we actually weren't able to find any distinguished signal of Knox for Ray Koki. There were only 753 strokes for the Ray Koki eruption, which sounds like a lot, but it was over about 18 hours. And compared to, for example, Krakatoa, there were over 30,000 strokes. Longer time frame, but orders of magnitude more strokes. So I think Knox is a really cool avenue to investigate, but I haven't gone down that route yet.
Thanks. Looks like we have another question in the chat here from Colin Rowell. Colin asks, are there any good particle size distributions for an Krakatoa? Is it possible to examine the relationship of lightning intensity with fine ash content? For example, might the mass eruption rate lightning relationship be more obvious if you account for percentage of fine ash?
it's highly likely that that relationship is there. There's been experimental work by Damien Gaudin at LMU, where he showed that you can't get discharges at all in a shock tube unless you have fine ash present. So fine ash definitely plays a role. As far as particle size distributions, I haven't worked with the ash samples that were collected there. Those are being handled by Sam Engwell and Sebastian Watt over in the UK. I'm pretty sure they're putting in a AGU abstract, so I will rep that for them. And so they would be the ones to ask about the ash distributions.
And Alexa also notes that the amount of external water is also likely to be important in chat. So.
Yes.
All right, any other questions, comments, discussion? This is really fantastic, Cassandra. I think you've provided a great overview of all the physics and your observations. The conversation will continue on Slack if you'd like to join that. And let's thank Cassandra again, and I'll leave this chat open for a few minutes if people want to have a smaller discussion.